Hello and welcome back. So about a year ago I made a video on Convergent Divergent nozzles, mostly as a response to makers that I was seeing just kind of slap a Laval nozzle on a random project and not actually understanding how to design one or whether one was even a good fit for their project. So I tried to make a resource with equations and information so you can determine if you need a Laval nozzle, and if you do, how do you actually design one? But one thing I missed in that video was an intuitive explanation of why you want to converge and then diverge once you achieve supersonic flow to keep accelerating your flow, which is not intuitive at all, and I kind of glossed over and just shared the equations. So that's why I'm making this video. This is a more intuitive look at why a nozzle converges then diverges without all of the math from the original video. Okay, maybe we'll multiply a couple numbers, but that's pretty much it. So to explain this, I'm going to start from base principles about what's actually happening in this flow. Very simple things. The first thing is, how does a rocket work? Why does it accelerate? Well, the simple answer is the conservation of momentum, or every action having an equal and opposite reaction. Imagine a spaceship in space that weighs 1 ton and has 1 ton of propellant. You then burn that propellant, run it through your engine, and accelerate it to several kilometers per second. According to the conservation momentum, now that your propellant is moving that direction very quickly, your rocket ship should also be moving in the opposite direction at the same speed because they have the same mass. The very simple math behind this is that momentum, mass times velocity, is conserved. So if you have the mass of the ship times its velocity, which is initially 0, and the mass of the propellant times its velocity, which is also initially 0, that sums to 0 net momentum. Then after you burn the fuel, that amount of momentum has to be conserved. So now that you've added some velocity in one direction for the propellant, you need velocity in the opposite direction for the ship. And these positive and negative velocities cancel each other out, giving you again 0 momentum, but now your ship, which you actually care about, has been accelerated without having to react against the ground or air like you would with the propeller. And this simple fact leads us to the next important part of rocket engines, which is that faster exhaust velocity is more efficient. If you take that 1 ton propellant and accelerate it to 10 kilometers per second, now your rocket ship is going 10 kilometers per second as well, so much faster than it originally was. Basically, the faster you can blow your exhaust out the back, the faster your rocket's going to go, and the more efficient it is per unit of propellant. This is why exhaust velocity is a driving factor of your specific impulse, which is a measure of your efficiency. Click here to learn more about that. So to make an optimal rocket engine, we basically start with a tube that's blowing a certain amount of fuel through it, and we want to accelerate that to the highest velocity possible. Now, if we're starting at subsonic speeds, this is really simple and intuitive. You take a big pipe with a certain amount of fuel flowing through it, and then you choke it down to a smaller hole. Now the same amount of mass has to go through that small hole that was originally going through the big hole. More velocity means more thrust, higher efficiency. Now, maybe that isn't super intuitive why that would create more thrust, because of course what's actually pushing you forward is the pressure of the fluid or gas inside of that tube. So you would think if you just left one end open, all of the pressure is pushing you that way. If you partially close one end, there's some pressure pushing against that, creating negative thrust. So why does a convergent nozzle increase your thrust if it's putting something in the way of the flow that's actually apparently creating some drag? And the answer is the nozzle itself is creating more back pressure. If you cut the nozzle off, all of this fluid can flow out much more easily because it's not constricted. So that decreases the pressure in your combustion chamber, decreasing your thrust. So the actual mechanism for a convergent nozzle increasing your thrust is increasing the back pressure in your combustion chamber. This is sort of an alternative way of looking at how a rocket engine works. Instead of looking at accelerating the exhaust, you're looking at increasing the pressure, and that higher pressure on your injector phase means more thrust. But the problem is, once you exceed the speed of sound, a convergent nozzle cannot create back pressure. The speed of sound of a fluid is how fast information can travel upstream. So when your pipe's getting smaller, that is constricting the flow, and that information is flowing back upstream all the way to the injector face and essentially telling it, hey, there's too much gas here, here's a bunch of pressure, and it's pushing you forward. But once the flow is going faster than its own speed of sound, that pressure wave cannot get back into the engine to tell it to have more back pressure. So if you keep making it smaller, you don't exceed the speed of sound, you slow the gas down upstream because there's no other way for information to get back upstream. So this puts a hard limit on your specific impulse for a convergent only nozzle. You reach the speed of sound, and if you make it any smaller, you decrease your mass flow. You don't increase your ISP, or exhaust velocity. But that doesn't mean you're done. You still have leftover energy in your flow that you can use. If you were to cut a rocket engine right at the throat, yes, you would have, I guess not supersonic, but sonic exhaust coming out very quickly, but you would also see it expand as soon as it left because the pressure of the gas is higher than the pressure of the environment. And that extra pressure causes it to puff up and expand. And that's visually showing you there is more energy in your exhaust than you're using. And of course, we know we can't just keep converging. Like I just said, that information can't travel upstream and create more back pressure. So we have to find another way to use that pressure. And here's where a divergent nozzle actually becomes super intuitive. That gas can't send information back upstream, but it can send it out to the sides and push against the walls of the container. If you have a tube with supersonic flow, of course there's still pressure pushing on that tube. And it's that mechanism that we're going to use to create a little bit more thrust and make our engine a little more efficient. By angling this boundary, that outwards pressure has a small component in the forward direction where we want our thrust to go. And as it expands, that pressure decreases until the pressure has equalized between your fluid and the environment. If you're in space, the environment's zero pressure. So in theory, you can keep making this bigger and bigger until the weight of the nozzle exceeds that small amount of pressure that's adding a little more thrust. And here's where we go back to the conservation momentum. I just explained why a divergent section of supersonic flow would create thrust. But why would it accelerate the flow? Well, simply put, to create thrust, the flow must go faster according to the conservation momentum. Your exhaust has to be going this direction faster, or else it wouldn't make sense for you to have any more thrust. Now, of course, if you dive into the math really deep, you can find a more precise explanation of the mechanism. But at least in my head, that makes perfect sense. The flow must accelerate because it's producing thrust. But of course, the question is, why doesn't a divergent section accelerate flow at subsonic speeds? And the answer is that information can flow back upstream. The actual particles of fluid coming through this tube into the expanding section are crashing into each other because they can. They're not exceeding the speed of sound, so they're interacting and they're bunching up, creating higher pressure but slower flow, and even creating large vortices if you overexpand it too much. I showed simulations of this in my original video of just how messy the flow can get when you try to expand subsonic flow. Anyway, I hope this is a much better explanation of why a convergent divergent nozzle creates more thrust than just a convergent nozzle. Your flow is constricted, causing more back pressure, but exceeds the speed of sound, so it can't create more back pressure because information can't travel. So you produce more thrust with the leftover pressure you have by expanding it against an angled surface until the pressure is equal to the environmental pressure. And according to conservation momentum, this little bit of extra thrust means you'll get a little bit of extra velocity in your fluid. But anyway, thank you for watching. I'm Con Hathi, and I'll see you in the next video.